We're all drowning in data these days. It's everywhere. But how do you turn all of that noise into a clear signal? Well, today, we're going to look at a surprisingly simple tool that can take a complete mess of numbers and make it tell a clear, understandable story. Let's dive in. So here's the plan. First, we're going to face the problem head-on, just a jumble of raw data. Then, we'll learn the lingo of our solution, the frequency table. After that, we'll actually build one from scratch, see how it lets us make some really powerful comparisons, and then we'll wrap it all up by solving a fun little data mystery.
All right, so why even bother with any of this? Because raw numbers, all by themselves, are pretty much just chaos. They're overwhelming, and honestly, they don't really tell you a thing.
Check this out. What you're looking at are a bunch of daily commute times, in minutes, for people in Los Angeles. Now, just by staring at this jumble of numbers, can you tell me what a typical commute is, or how many people have a really long drive? It's almost impossible, right? This right here is what data chaos looks like. So the solution to this mess is something called a frequency distribution. And don't let the name scare you. All it is a simple table that groups the data into sensible categories. We call them classes, and then just counts how many data points fall into each one. It's a really elegant way to bring order and clarity almost instantly. Okay, so before we can build one of these tables, we've got to learn its basic parts. Let's just quickly go over the essential vocabulary so we're all on the same page. Every category or class needs clear bookends, and we call these the class limits. So for a group like 15 to 29 minutes, 15 is the lower class limit and 29 is the upper. Simple as that. They just tell you the smallest and largest values that can fit inside that bin. Now, you might notice that there are these little tiny gaps between our classes, like between 29 and the start of the next one at 30. Well, class boundaries are what fill those gaps. Think of a number like 29.5. Their whole job is to make sure there are no holes in our data, which is super important if we ever want to turn this table into a visual graph later on. Sometimes you need just a single number to represent an entire category. That's where the class midpoint comes in. It's just the value right smack in the middle of a class. You find it by just averaging the upper and lower limits. Easy. And finally, class width. Now, this one is absolutely crucial for actually building the table. It's simply the size of each category, the size of each bin. You find it by looking at the difference between the start of one class and the start of the very next one. Getting this right is the key to making a table that's consistent and easy to read. All right, vocabulary lesson is over. Now for the fun part. Let's actually take that chaotic mess of LA commute data and build our own frequency distribution, step by step. It's a pretty straightforward 6-step process. We're going to decide on how many groups we want, calculate how wide each group should be, pick a good starting point, lay out the whole structure, and then, the final and most important step, actually go through our raw data and tally everything up. So to figure out our class width, we take the highest value in our data, that's 90, and subtract the lowest, which is 5. Then we divide by how many classes we want. Let's just say 7 for this example. The math gives us 12.1, but counting in intervals of 12.1 would be a total nightmare. So we make a practical choice and round up to a nice, clean, convenient number like 15. Now that we have our class width of 15, building the table structure is a breeze. We can start at a convenient number like 0. So the first class is 0 to 14. The next one starts at 15, then 30, then 45, and so on. And just like that, we have the whole skeleton of our table ready to go. And after we tally up all 50 of those data points, there it is. The chaos is gone. We can now see instantly that the most common commute time is in that 15 to 29-minute range. And we can also see that those super long commutes, the ones over 75 minutes, are really rare. This is a perfect example of how creating a little structure reveals the hidden story. Okay, so organizing one set of data is great, but the real power comes when you want to compare two totally different sets of data, like, say, commute times from two different cities. To do that, we use something called a relative frequency distribution. All this means is that we replace our raw counts with percentages. Now, why is that so important? Because it lets us make a fair apples-to-apples comparison even if our two groups are completely different sizes. So here we go. We've got commute times for New York and Boise side by side, shown as percentages. And wow, you can immediately see the difference. Just look at those first two rows. The The percentages for shorter commutes in Boise are way, way higher than in New York. And this slide really drives that point home. In New York, less than 30% of people get to work in under half an hour. But in Boise, a whopping 75.8%, a huge majority, have that shorter commute. Using percentages makes this massive difference jump right off the page. Okay, it's time to put on our detective hats for this last part. Because sometimes a frequency distribution doesn't just organize your data, it reveals a totally hidden story. So this table shows the weights of a random sample of US pennies. Now take a close look at that frequency column. We have a group of lighter pennies, then a big gap, 0, 0, 0. And then another group of heavier pennies. Now that is very strange. So what's the story here? A gap like this in your data is a massive clue. It's screaming at you that your data might not be one uniform group, but could actually be coming from two, or maybe even more, completely different populations all mixed together.
And that is exactly what's happening. Turns out, back in 1983, the US Mint changed how they make pennies. The older ones are mostly copper, so they're heavier. The newer pennies are mostly zinc with just a thin copper coating, which makes them a lot lighter. Our frequency distribution didn't just organize the weights, it uncovered a piece of American history.
So the big takeaway here is this. Whenever you build one of these tables and you see a major gap, it's like a giant red flag. Your first question should always be, wait a minute, am I looking at two completely different groups that have been mixed together? So from chaotic commute times to the secret history of pennies, we've seen how a frequency distribution is a simple but really powerful tool for finding clarity. It definitely makes you wonder, doesn't it? What hidden stories are just waiting to be discovered inside your data?